This is the second part of section 7.5, example problems. We are solving trigonometric equations. And in the examples we've been finding solutions in both radians and in degrees. So this is problem number 6. This time we want to find solutions in both 0 to 2 pi and also between 0 degrees and 360 degrees. So for this example, we're going to look at 2 sine squared of theta plus 7 sine theta equals 4. This looks like a quadratic because we have sine squared as one of our variables. And to solve quadratics, we move everything onto one side and 0 onto the other. So I will subtract 4 from both sides so that I can hopefully factor. If we need to do a variable change, we always take whatever's in the middle, and I'll call that m. Let's let m equal the sine of theta. So then we have 2m squared plus 7m minus 4 equals 0. And this factors into, let's see, 2m, m, I think we'll have minus 1 and plus 4. Yeah, that works. And we use the zero principle to split this into 2 different equations. Either 2m minus 1 equals 0 or m plus 4 equals 0. Going back to our variable exchange, we have 2 times the sine of theta minus 1 is 0, or sine theta plus 4 equals 0. So starting with the equation on the left, we will add 1 to both sides and then divide both sides by 2. And we'll come up with the different solutions for when the sine is equal to 1/2. I think sine is equal to 1/2 at pi over 6 and also at 5 pi over 6. So theta will be pi over 6 or 5 pi over 6. For this second equation on the right, moving that 4 to the opposite side, we get that sine of theta is equal to -4, and this is not possible. Sine doesn't take on a value of greater than 1, so we don't have any solutions for that point. So we'll just take these single solutions. Those are the radian measurements. The degree measurements would be either 30 degrees or 150 degrees. So that'll be our solution for that problem. For the next problem, we're going to be looking at values that are not on the unit circle. So let's solve sine of x plus 3 equals 2.0816. I'll start by subtracting 3 from both sides. And then I have that sine of x is equal to -0.9184. Just double check that. 2.0816 minus 3. Yeah. So we don't know, this value is not on the unit circle. So what we're going to plug into the calculator is sine inverse -0.9184. And this will give us a solution. Let's do this rate. I'll do this twice. I'll do this once in radian mode and then once in degree mode. So this first one we'll do radian mode. And what does this give us? This is telling, we're plugging in the value of the sine, and then it's going to give us back what the angle is that's associated with that. So sine inverse negative 0.9184, and I am getting negative 1.16. I guess I'll go to 4 decimals. 40. But our solutions are supposed to be between 0 and 2 pi. So I'm going to add 2 pi to get into the range that we're looking for. So I'm going to add 2 pi to this. And I'm going to end up with plus 2 pi. 5.1192. So that's one of my answers. Now let's think about where these answers are on the circle. We know that pi over here is 3.14. And then if we did pi over 2, that is about 1.5708. So negative pi over 2 would be about negative 1.5708. So this original value, negative 1.16, is somewhere over here, right? This is where negative 1.1640 is, and that's also the same as 5.1192. We just found that by going around the circle one time. And so what I'm wanting you to think about is that this value that we're getting is actually the length of the arc right here. That's this distance is this distance or arc length is 1.1640. We just have a negative sign because we're going clockwise or backwards around the circle. So we're going to use that information to find the second answer. We're looking for the sign being negative, the y value being negative. So that means that that's going to be in quadrant 4. We already have that answer, and also in quadrant 3. And we always take that distance from the x-axis down. And so we want that arc length to be the same. This is going to be 1.1640. This distance is also going to be 1.1640. So to get this answer, we're going to have pi plus 1.1640. So I'll do that calculation now. Pi plus 1.1640, and I'm getting approximately 4.3056. So putting both of these together, I'm getting that my solutions, let's see, the variable was x. My solutions are x equals 4.3056. That's one answer, and the other is 5.1192. I could follow this same process for degrees. Let me go back to what we had. Let me copy this. Okay, so let's redo this in in degrees. Let's use a calculator in degrees. If we plug this in degree mode, we're going to get hang on a second, I gotta get my calculator. Okay. Negative 66.69 degrees. So similar to what we kind of saw before, we know that that is somewhere over here. We add 360 degrees to that to get that to be a positive value. So plus 360. And we get 293.31 degrees is one of our answers. Now this distance here is 66.69. And so we're going to go this way, 66.69 degrees to get our second answer. So our second answer is 180 degrees plus 66.69 degrees. Which is 246.69. So our solution in degrees is 246.69 or 293.31. Okay. New page. Number 8. Let's find all solutions in 0 to 2 pi. I'm going to switch to do these last few examples just in radians because most of the time in calculus you use radians and not degrees. Sine of 2x times cosine of x minus the sine of x equals 0. In this particular example, we have a double angle and then we also have the single angles. We need to have all of the angles match, and right now they don't. So what we'll do is use a double angle formula to switch it. We're going to switch this into 2 times the sine of x times the cosine of x, right? And then we'll still have multiplied by the cosine of x minus the sine of x equals 0. This is 2 sine of x times cosine squared of x, cosine times cosine. And then what I'm going to do is factor at this point. I'm going to see that in the two terms that I have, they both have sine of x in them. So here's one term, here's another term. So I'm going to pull a sine x out to the front. And I'm left with 2 cosine squared x minus 1. I just divided both terms by sine of x, pulled that out to the front. I've got 2 items that are being multiplied together that equal 0, so I can split them. I can say that means that either sine of x is equal to 0 or 2 cosine squared x minus 1 is equal to 0. The sine is equal to 0 when x is equal to 0 or pi, right? That's when we have sine being 0, when the cosine is either equal to 1 or negative 1 here and here. So that'll be our two solutions for that set. And then going to the equation on the right, I will add 1 to both sides. 2 cosine squared x equals 1. Divide both sides by 2. Cosine squared x is 1/2. And then I'm going to take the square root of both sides. And when we do this, we have to remember to put a plus or minus for the value of the number. So the cosine of x is plus or minus the square root of 1/2. Now, if you plug this into your calculator or try to simplify it, what it's going to tell you is that this ends up being square root of 2 over 2. So for these values, we are thinking about positive root 2 over 2 is either here or here, and the negative root 2 over 2 is over here or here. So the solutions here are x equals pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. They're all the quarter points. So putting those two things together, we get our solution set. So the solution are going to be that, and then also this together. That's all of our solutions. All right, let's do another example like that. Number 9. Sine of 4x minus 2 sine of 2x equals 0. The two angles that I'm considering are not the same, right? So I'm going to change the first one to look a little bit different. I'm going to put it as 2 times 2x. So then I can think of this as a double angle, right? The angle is here, and then this is right here, this is doubling it, right? So using the double angle formula, I have 2 sine of 2x times cosine of 2x. This all came from here. And then we'll leave the second term alone. Okay. Now, both of these two terms have some things in common that could be factored out to the front. So I'm going to factor out a 2 sine of 2x out of both terms. And then I'm left with cosine of 2x minus 1. And then I can split these into two separate equations. I have either 2 sine of 2x equals 0 or cosine of 2x minus 1 equals 0. Looking at the equation on the left, dividing both sides by 2 really isn't going to make a difference, right? Because I'm going to end up dividing 0 by 2, which is okay. 0 divided by 2 is just 0. So I have sine of 2x equaling 0. And so I just want to know, when does the sine equals 0. Sine equals 0 at hang on, we need to pause for a second. We need to think about, let me go back up for a second. So we're finding solutions. We're looking for solutions in 0 to 2 pi. That means that x is in between 2 pi and 0. But when I'm looking down at where we are, we have double, right? We have double the angle. So if I change this to 2x in the middle, multiply all of these by 2, that means that now my range is actually extended to 4 pi. When we have a 2 that's with the angle, that changes the period of the, and so we're having we're having more solutions than we would consider to begin with. So we're going to look at anything that's between 0 and 4 pi. So back here, sine is equal to 0 when the angle is either equal to 0, so the angle is either 0 or pi or 2 pi or 3 pi. Every time that we're at one of the axis points, that's where we're going to have the sign being 0, here and also here. I'm not going to include 4 pi because that's not in the range. Oops, I made a mistake here. This should not be equal. We have not equality on the upper bound, but equality on the lower bound. 4 pi is not included, so I'm going to stop at 3 pi. But the angle that we have is 2x. 2x is either equal to 0 or 2x is equal to pi, or 2x is equal to 2 pi, or 2x is equal to 3 pi. So we'll solve each of these for x, and that gives us that x is 0, or x is pi over 2. Here we'll have x is equal to pi, and here we'll get x is equal to 3 pi over 2. So this is our set of solutions for the left-hand side of the equation. We're back over here to the right side. Cosine of 2x minus 1 is equal to 0. Let's add 1 to both sides. And we want to know when the cosine is equal to 1. Cosine is equal to 1 only in one place, which is here, right? But we're going to consider all the options between 0 and 4 pi. So the angle is either going to be 0 or 2 pi. We're not going to go around again and include 4 pi because that's not included in our range. So the angle is 2x. So 2x equals 0 or 2x equals 2 pi. And this one gives us x is equal to 0. Well, that's already one of the solutions we had. And this one gives us x is equal to pi. That's also one of the solutions that we already had. So it looks like our solution set is complete back here. We had some repeats in the other equation. Okay, I'm going to get a new page to do 2 more examples. Now, when you're doing problems like this, you often want to make sure that you check the answers at the end to make sure that they actually make the equations true. All of the examples I've done, the solutions do check, but I'm going to give you one example in just a moment where the solutions do not check, and it's a very specific example. I'm going to do one more example first on this one involving multiple trig functions simultaneously. And so I just have 2 more examples to show you. So this is example 10. Tangent squared x plus 4 equals 2 secant squared x plus tangent x. And we want to find all solutions in 0 to 2 pi. Now we've got two different trig functions, and so what we need to do is make an exchange. And so we're going to use one of the Pythagorean identities so that we can get rid of the secant squared that's here. We're going to switch this out. We're going to switch that out for 1 plus tangent squared. Right, so we're using a Pythagorean identity. Plus tangent x. And on the left side, we're just going to keep this as it is. Okay. Next, I'll distribute the 2 to both items. And now because I have a quadratic, I'm going to move everything onto one side, 0 onto the other so that I can factor. In this example, I'm going to move everything to the left because I have a 2 here and I'm going to end up subtracting the tangent x from the left-hand side. And if possible, you want to keep the squared term positive. So I'm going to subtract 4 here, and I'm going to subtract tangent squared x here. So we're going to end up with 0 equals -2 plus tangent squared x plus tangent of x. And then rearranging, I have tangent squared x plus tangent x minus 2. This has the structure of m squared plus m minus 2, which factors into m minus 1, the quantity squared. Oops. I said m and I wrote x. No. M minus 1, m plus, oops. Goodness, give me a second. Okay, plus 2, that's better. So I have 0 equals tangent x minus 1 and tangent x plus 2. And then we'll split this into 2 separate equations and solve them separately. Okay. So for the one on the left, tangent of x equals 1. That happens, that's one of the ones that's on our unit circle. That happens at pi over 4 and 5 pi over 4. So x is pi over 4 or 5 pi over 4. For the equation on the left, tangent x equals -2. That's not on the unit circle, so we're going to plug this into the calculator. In radian mode. You're going to plug in tangent inverse -2. And when we do that, tan inverse -2, I'm getting, oops, I'm not in radian mode. Hang on, give me a second. I'm getting -1.1071. But I need to add 2 pi to get this to be in the positive range. So I have 5.1760, which is in the fourth quadrant, right? Yeah, it's gonna be about here. And this distance is 1.1071. We get that from there. So tangent is negative in this case. It's negative in quadrant 4 and also in quadrant 2. Remember, we always move from the x-axis into the quadrant. So to find the other value, I'm going to start at the x-axis and move this distance to find the other solution. And so to get that, I have 180, pi minus 1.1071. So our second solution is pi minus 1.1071, 2.0345. So all my solutions, putting them all together, x equals pi over 4, 5 pi over 4, 2.0345, and 5.1760. Even though there aren't the pi symbols written in them, when I have a number without degree symbol, that is a radian measurement. Okay, I'm going to get one last clean sheet, and this is the last example I'm going to do. Again, all the examples I did in the past up for today, all the values, check. If you go back to the original equation, plug them in, they will make the equations true. The time that you have to proceed with caution is if there's a square root involved, because to get rid of the square root, we have to square everything, and that creates artificial solutions because you're taking something that could have been negative and changing it to be positive. So in this example, we're going to find all solutions in the range from 0 to 2 pi. And our equation is square root of 3 times the cosine of x minus the sine of x equals 1. Before I square everything, I want to move the two trig functions away from one another, because if I square what I have on the left side now, I'm going to end up with a bunch of terms that I'm not wanting. So I'll start by adding sine of x to both sides. And I'll get square root 3 cosine of x equals 1 plus sine of x. Now I'm going to square both sides. Sorry, I had to pause temporarily because my husband was trying to make a cup of espresso, which is really loud. I digress. Okay, we're going to square both sides. And when we do that, on the left-hand side, we have two things that are multiplied. So I'm going to square the square root of 3 as it is. When I square square root of 3, I just end up with 3. And then cosine is going to be cosine squared x. These two terms are multiplied together, so I'm just going to square the first one and square the second one. I don't have to do anything different for those. But for the right-hand side, when I square this, I have to square the first term and square the last term. And then we multiply the two terms together and we double, right? So this is 2 times the sine of x. If you need to convince yourself, you're just going to write this out. You would write out 1 plus sine of x multiplied by 1 plus sine of x, right? And multiply the whole thing out. All right. Well, now I've got two different trig functions. So I'll use a Pythagorean identity to change the cosine squared into sine. I want to get everything into sine. So we'll rewrite cosine as 1 minus sine squared x. Right? That's a Pythagorean identity. And then we'll distribute that 3 to both terms. And then what I want to do is move everything onto the right-hand side because I have a quadratic and I want to have it equal to 0. So I'm going to subtract 3, and add 3 sine squared x. Subtract 3 minus, oh no, I want to move everything to the left, don't I? Let's think about this. If I subtract that, that's going to be minus. I want to go the other way. I want to move everything to the left. So instead, we'll subtract 1. No, I was right the first time. Oh my goodness. My husband came and got me all discombobulated. Goodness. Minus 3 plus 3 sine squared x. Minus 3 plus 3 sine squared x. Okay, better. So we have 0 equals negative 2 plus 2 sine of x plus 4 sine squared of x. Okay, I'm going to rewrite this. 4 sine squared x plus 2 sine x minus 2 equals 0. Okay, now let's factor this. This is in the format of 4m squared plus 2m minus 2 equals 0. We could definitely pull a 2 out to start, right? 2m squared plus m minus 1. So then this is 2m minus 1 and m plus 1. Let's see, does that work? Yeah. All right, so changing back to sine, we have 2 times 2 sine of x minus 1 times sine of x plus 1. We have 3 different things multiplied together equaling 0, right? We know that this can't equal 0, so we can ignore it. So we'll just take the other 2 and say, well, we either have 2 sine of x minus 1 equals 0, or sine of x plus 1 equals 0. This gives us 2 sine of x equals 1, or sine of x equals 1/2. Sine of x is 1/2 when x is pi over 6 or 5 pi over 6. On the other equation, sine of x is equal to negative 1, and that happens when x is at 3 pi over 2. So now what we have to do is check all of our solutions. The original equation was square root of 3 times the cosine of x minus the sine of x equals 1. So let's check 5 pi over 6. Square root of 3 times the cosine of 5 pi over 6 minus the sine of 5 pi over 6. The cosine of 5 pi over 6 is root 3 over 2, negative root 3 over 2. And the sine of 5 pi over 6 is 1/2. So multiplying this together, I have negative 3 over 2 minus 1 over 2. This isn't going to equal 1, right? This does not equal 1. So we reject this solution. It doesn't work, and it was created artificially because we squared everything. Let's check a different solution. Let's check pi over 6. Square root of 3 times the cosine of pi over 6 minus the sine of pi over 6. We want to know if that equals 1. Square root of 3 times square root of 3 over 2 minus 1/2. We have 3 over 2 minus 1 over 2. Yeah, that one actually works. It ends up being 2 over 2, which is 1. So this one works. So we keep this solution. And then our last solution, check 3 pi over 2. Square root of 3 times the cosine of 3 pi over 2 minus the sine of 3 pi over 2. Does that equal 1? Square root of 3, cosine of 3 pi over 2 is 0. And the sine of 3 pi over 2 is negative 1. So I end up with 0, and minus 1, that changes to plus 1. That equals 1. So we keep this solution as well. And all, technically, like I said before, in all the examples that I've done before, you should check, but really the only time that we create these artificial solutions is when we have something where we've squared both sides of the equation. All right, those are plenty of examples for section 7.5. Have a great weekend, and we'll do a couple sections from chapter 8 next week.